So I didn't bring slides. I brought some toys to pass around. So my plan was just to kind of go through the design methodologies and reasons that we focused on for superior performance in this class. So most APs are built on Atheros, Qualcomm Atheros radios, all built to reference designs, with the exception of Cisco, which is on top of Marvell radios, customized to Cisco's requirements. So we use Qualcomm as well. Our goal, and my team, right, we've been at Trapeze for, I didn't come from Trapeze, but so I lead the hardware design team for the campus and data center business unit. And the Trapeze team has been working on since Wi-Fi became Wi-Fi, right? So we've got a lot of depth and experience on Wi-Fi. And our design methodologies and goal with the 532 access point was to be the best performing access point in the industry, for that class of product at that time frame, right? Because we're always jumping and leapfrogging each other. And so we went after a couple design areas we were intending. And it's really the whole, the overall use case of the product. And one of the key methodologies was RF performance. How can we maximize RF performance? And so we focused on two areas in RF performance. One is the RF amplification circuitry on the radios, and the other area is on the antennas. Because the antennas give you double the bang for the buck, right? They enhance your transmit and your receive. But the radios, the receive performance, we can't do much about because that's embedded in the circuitry, and that's pretty much the same for everybody. But we can enhance what the radios are receiving on the antennas. So we spent a lot of focus on our antenna design, and I'll pass this around after. But with the 3-stream radio, right, performance, we want to optimize performance on all 3 streams. And so how do you do that? You need to maximize the diversity of the signal. You need to maximize the signal difference on the power levels and the phase difference that the radios are receiving on each signal, so they can maximize the bits, the data rate per chain and stream. So the way to, there's a bunch of ways to maximize diversity, and the standard ways to do it, which we've incorporated, are pattern diversity. So right, every antenna, even though they say it's omnidirectionally in a uniform pattern, antennas they're not. I mean, they're generally uniform, but there's nulls and lobes all around the pattern. So we analyze that in the design, and we custom design the antennas. Every antenna in this access point is different from every other one, and we've tuned the patterns on the antennas so that the nulls on one antenna overlap the lobes on the other antenna, so that we're maximizing the difference in gain on stream that comes in on one antenna versus the other. So taking a standard antenna and multiplying it by 3 and shifting the position so that those nulls don't overlap, that's a standard technology. We've done that. And then we went one step further, where we actually tuned every antenna individually. And that's not something that's being done on standard reference designs. The next thing we did is, spatial diversity is another big way to diversify your signals, right? Because the signals are always summing and subtracting as they're going through space, and the sum total of any particular signal on all its reflection paths or the single reflection path is very different within the position on the access point. One wavelength at 5 gigahertz is about 2 centimeters. So that's kind of an optimum, and we can put these things at a half wavelength. So that's a half wavelength, or 1 or 2. So we noticed that all the antennas are out around the outer edge of the access point. Optimizing performance is just not RF performance, it's system performance. And if the system gets too hot, then the RF performance degrades. So we also had to position all the antennas so that they maximize the airflow, the convective airflow through the system. So a lot of thermal design analysis on this product. So we put the antennas out near the edge. Now we've got two types of diversity, very standard diversity. We've optimized them, a little bit more than standard. But Polarity Diversity is a third way, and systems that are cross-polarized can get between 15 and 30 dB of isolation between two signals that are polarized differently. That's huge. The standard position diversity and pattern diversity, we're talking about 2 or 3 dB. 3 dB is twice the power, right? So 30 dB is 2 to the 10th times the power. It's infinite as far as any of these guys are expected. So you can totally tune out one signal with respect to the other by using polarity diversity to an extent that you cannot with pattern diversity. So the problem with polarity diversity is vertically polarized antennas are tall. And how do you do that in an access point that you want to have short? So we spent a lot of engineering effort on developing vertically polarized short antennas. So another area that we looked at is the performance band balancing. So everybody has been doing band steering where we try and push somebody to 5 gigahertz. But a very annoying problem is your client, which is really making the band steering decision, and we're trying to guide them. Part of that decision is based on the signal strength. With the same antennas and the same transmit power, the 2.4 gigahertz signal, the AB, the BG band is going to be twice the power level at any given receiver of the 5 gig, right? The attenuation over the air, because the frequency is, the wavelength is twice as short of 5 gig, right? So it attenuates twice as much. And just over, pretty much any medium. So what we did is, normally you look at access points and the 5 gig antennas, you look in and you can tell what the 5 gig antennas are because they're half as small. Because the people tuned to maximize the gain and to make the gain common. That was just a design methodology. Well, we flipped that on its ear. And we made the 5 gig antennas the same size as the 2.4 gig antennas. And we figured out, and we positioned the antennas in the system where there was headroom such that we were optimizing the 5 gigahertz gain relative to the 2.4. So our 5 gigahertz antenna gain is, it's about 50% higher than the 2.4 gain in the system. We also...
So what is the gain of the antennas?
7 dBi. And it's about 3.5, 4 dBi on the 2.4.
So that's much higher than most of the other manufacturers.
It's very high.
Internal antennas, right?
So we had a lot of, there's a lot of discussion of, okay, we want to differentiate on performance. There's a lot of information or indications that active beam steering and adaptive antennas is a way to do that. We're looking at the active antennas, and aside from the huge software load that we didn't have the time we're trying to get to market to really go through and drive, there's the adaptive antennas. You go look up the FCC reports of our competitors, and I do. And the active antenna, the biggest gain one out there is 3 dBi. Right? So so they can put 3 dBi with, they say, a 7 dB difference, around in some certain sector size and patterns, and over 500 combinations or 2,500, depending on their access points. So ours is more than twice the power, twice the gain, than everywhere. So you get into, well, well, we don't need to go there. I'm talking about SAP, but if you want me to, I can go into why why we chose to do non-adaptive antenna as we thought it was a higher performance.
Adaptive antenna, you're referring to Ruckus approach?
Among the primary one, yeah.
The primary, well, the only one is at this moment that does this.
Yeah, so their antenna is a 3 dBi antenna, the ones that are shipping.
Well, the data sheet or the claim, it's from 3 on the lower end up to 7 on the higher indoor, up to 11 on the outdoor. So
I went and pulled their FCC reports where they have their antenna patterns, and their max gain is 3 dBi, and it goes down to like -6.
I don't know for the others, but my personal perspective is data sheet is okay. What we like to see is
how it really performs.
Performance. Yeah. And Ruckus does perform on the RF. It kills both Juniper and both Cisco and Aruba on the RF. It's not the overall performance, so it's
But
just
they don't have a
part of it.
3-stream out yet, right?
They have both outdoor,
When?
both indoor.
Okay. When did that come out? I've seen the presentations on it and their antenna.
It's just in the last couple of
A
years.
while.
Okay.
Actually, you have, as we have the reports, you have the Tom's hardware that has been done by by Joe.
I guess they were here
Bartels.
earlier today, so you're
also-
more up to
also
speed than I
the
was.
main- Their 2x2x2 outperformed 3x3x3s in most of the performance tests, but the close proximity test. So, yeah. But again, it's just one part of the equation. We are looking at end-to-end performance.
mhm.
Right?
Okay. Where was I? So you'll notice that the 5 gig radio is significantly larger than the 2.4 gig radio. So we put more money and more circuitry and bigger amplifiers, and we deviated from the reference designs on both these radios. The 2.4 we stripped out. Reference designs are dual band, so we stripped out all the 5 gig circuitry so we could get higher efficiency on the 2.4.
So you're using discrete elements for the amplifier, low noise amplifier?
Yes, the PAs are discrete PAs. Yeah.
So the results, normally 2.4 seems to travel further because it's got a bigger aperture, and the waves are bigger than, and the antennas are smaller. So you're saying you have much greater receive sensitivity on 5 gig because you have a larger aperture.
We have higher receive gain on the antennas, so we're giving a higher signal. We have the same receive sensitivity because the receive sensitivity is the circuitry that's in the radio.
So the energy touching the receive sensitivity
Is higher.
Is higher.
Yes, yes, exactly. Relative to the 2.4, and that was by design.
Is that bidirectional results too? For both? I mean, I
Yeah.
can see how by listening you better, but you get the same punch going out.
Yes, yes, exactly. So we get a little more punch going out because we beefed up the transmission system. So that'll give a little bit better relative downlink, and uplink it doesn't affect, but the antenna solution affects both. The bottom line on this is we needed to look at every single area in the access point. Another thing that we thought was important was the usability in the space. The existing the trapeze access points are this big, and then these ones are this big, and taking into account, and we did 62 different industrial design iterations on this thing and sent it out to our field force and got reviews and back and forth, and just very cognizant that this thing is sitting 4 feet over people's heads, and what's it do to the psychology of the workplace and where it's going in. So a lot of energy on really making it small. A lot of energy on quality. Return rates are nobody's friends. High return rates are everybody's enemy. To really put a lot into the quality process, design quality and test all through development. Our return rate targets here are 0.1% per year is the target we designed to. We don't know what the return rate is because we've sent tens and tens of thousands, hundreds of thousands of APs out, and none of them come back yet. So cross my fingers, but we've designed it for very high quality. And other access points that I know I've designed at past companies in the past. There was a period of about 6 years when Wi-Fi was starting where 5% was the average return rate on access points. I mean, that just kills your bottom line. It kills your customer's experience. It's terrible. And then there was a second phase of where we got down to 0.25%, and then now we're at 0.1. And I think that makes a huge difference in the customer experience. And I'll pass these around. I'll leave the box for people can dig through stuff later. So the other thing is ease of installation. We wanted to look at how easy are these to put up, and didn't really care about how easy they were to take down. They're pretty easy to take down too, but I figure once they go up, they're probably gonna stay there. And we designed redesigned the mounting methodology for a new user experience. Which one of these do I want to grab? I'll pass all these around too, and people can play with them.
Can we set of hands?
No, I'm good.
You who's gonna be the ceiling for you there?
Yeah.
I'll just be my own ceiling.
Useful here.
I mean, so,
Actually, if you can do it one
right.
time,
So
that would be great.
this bracket comes, with every AP. It fits the 11/16, the 15/16, the enclosed rail, the low profile. I've got that in here rail as well. And you just come in and clip it on. There's a release button here for the AP that you can put in a security screw with Torx head or whatever. So it's kind of a passive security. If somebody wants to take this AP off the ceiling, they're going to have to break the plastic, and it's not going to go back on, so you're going to know. So it's that level of security. Or they're going to have to go find a custom machine, a custom screwdriver, because we built a custom screwdriver to go in here, and you can buy kits of those custom screwdrivers.
Or you tin snip the rail out.
Right, but either way, any of that, it's been tampered with. So it's the FIPS methodology where it's been tampered with, and that's the level of the security that we designed for. And so then,
Work with this kind where the actual ceiling tiles are down.
These are recessed.
Is that
so you'll see when you
Oh, okay.
went around
I
that
see.
there's a recess that in the bracket that fits up inside that recess. So that's one of that's the narrower one. This is that's the 11/16, and this is the 15/16. And then it just snaps on. And if you lock that pin here, and then you can't even see it's there, so you got to know it's there to release it. And it's pretty secure, it's very secure. And then you push the button and it comes out. We've gotten really solid feedback from our customer teams on just the ease of installation, which is what I was aiming for. We've got a wall box if you want to stick it on the wall. It has to extend out. The minus of going out the back of the AP, which is better from a seeing cable standpoint, is that now you can't bend the cable, so you got to have a bend radius. So that's why it sticks out from the wall. It just drops in. There's a button at the bottom, the same tooling. We have a North American wall box, so they can set it in the wall, and the cable bend goes in the wall and goes wherever it was routed. And then somewhere in here, there it is, a European wall box for our plenum rated external antenna AP. We've got a bracket that will sit on top of. It mounts on top of the plenum up in the plenum. So we're really trying to think about the entire customer experience for the diversity of use cases that are out there, and really make the whole installation and then performance and use the best. I said we're very competitive, and we want to win, and we win when people are going to buy our products.
You should send the brackets to Blake.
You're watching Twitter as we're just making this
I've been
comment.
reading the blogs as well.
Yeah.
So he has a comparison with pretty much every vendor about the brackets. So
Oh.
it should be interesting.
I have a
how-
drop-down ceiling in my home office that I mount
Oh,
all the
He
cool.
doesn't have a life, so.
I love my Slovenian friend.
I had one partner tell me it was a 60-second install per AP, once they know where they go, and the cables are there.
So that's the 532. This is the 322. This is based on a system on chip. So there's one radio and a CPU in the CPU system on chip complex, and then there's a second radio out under this can. And this does not have polarity diversity in the ceiling mount. We put the antennas on the PCB. This is aimed at we worked with the PLM team and said, for the use cases where this is going to be used, what's the maximum performance that you want to drive? And then we designed to that performance at the absolute lowest cost possible.
Jay, can I send these around?
Yeah, please.
So what is the list price of the devices?
List price of the 532 is $1095. And you're going to catch me on the 300 series.
195 and 395.
Okay.
And so there's not much different. So the similar design methodologies. I put the antennas, the polarity of the antennas, 90 degrees off from each other on the board. So if it's wall mounted, you got polarity diversity. And I think the polarity diversity is so important because the polarity on the clients is different. Like your laptop there is probably going to have 2 antennas in the side of the screen, and it's going to have 1 along the top. Right? The Apples are going to have 3 along the middle of the bar that are all horizontal. So when we design the polarity, we put 60%, 66% of our polarity direction we put horizontal in the stand, and then 33%, 1 in 3 antennas we put vertical of the 6 antennas that are in there. So there's 2 vertical and 4 horizontal. And then for like handheld devices, they're all single stream right now, and a lot of times they'll be horizontal or they'll be at an angle, rarely totally vertical. But there's always a lot of times there's a vertical component as well. And the polarity changes when it bounces off multipath. So really maximizing your polarity is a good way to maximize your signal. Yeah.
Do you like MRC the 2 polarities back together?
No, we use the polarities to segregate the streams to maximize the signal to noise. So treating the other stream as noise on the first stream and vice versa.
And so that is how you get.
Have one stream, it's going to match up against whichever one is most closely aligned with there.
Whichever one gets the biggest signal.
So that is how you get the 30 dB differentiation between one and another.
Yeah, these guys, the polarity diversity is probably more towards the 15 dB side, because but for outdoor customized big monster antennas, they get up north of 30 dB. But the challenge was to do that in a low profile, because I've been involved and seen taller APs that go, and in a lot of places they don't look as nice. And if you can get an access point that's higher performance and it's smaller and less obtrusive, that's what I'd buy, and that's what some of our customers are starting to buy too, right? And so that's our goal. You want to pass this around?
And we'll leave the brackets and stuff here so you guys can play with them and look at them later on while we're drinking beer.
So yeah, I've got you can pass this around too. So this is the 522.
So is there any naming convention to the APs? Does the 532 mean anything, or is it just?
So the Vinod came up with these. You want me to say, or I'm mic'd, so I'll say it. But there's a series. So the 300, the 500 series are kind of performance levels. 600 is outdoor, and then the second number is the number of streams. So the 22 and the 21 are 2 streams, and the 32 and so the 522 is 2 stream, and then the third digit is the number of radios.
Okay.
So 321 is 1 radio, and 322 is 2 radios. Okay. Any questions or?
Yeah, Jay won't be able to stick around for later, so if you've got questions, now's the right time.
Thank you, it was very informative.
Yeah.
All right. Hey, thanks guys.
Jay.
Thank you.
So
If you leave your toys, we'll make sure we get them back to you.
Feel free to abuse this stuff as much as you want. It's pretty robust.
There's one point that Jay didn't cover. I'll cover real quick, and you can answer questions
Okay.
they pop up. And that is, before I ask that question, let me ask the question. In a PoE switch, what's the #1 failure point of that switch? Power supply. When they designed this AP, it is the lowest power consumption of any 3-stream dual band radio on the market.
So what is the power?
Less than 10 watts. Full-blown running, right?
Yep.
I know a couple that do better.
Three stream?
Yeah, it's.
And dual radio?
8 to 9. Yeah. But that's impressive, anyways. Both. You have.
The object.
Most of them are 20 or whatever. So
Yeah.
Or a lot of them
when
are
they start adding AC,
12.95.
or higher.
That I've
with
designed
AC.
in the past because we want to just stay under the
Yeah.
AF power limit.
So that part of that object was, I mean, typically it's inversely proportional. When you get performance, you have more power, or you get bigger. So they managed to do all 3 of these, reduce size, reduce power, and get more gain out of it all at the same time, which was commendable to the team. So.
9 watts was on a dual radio AP or single radio?
Come again?
3-stream operation, your 9 watts was it a dual radio AP?
Yeah.
Or a single radio AP?
Dual radio. Well, it again depends. What are you using at the moment?
Yeah, exactly. So if these things are plugged up, conducted to a Verwave, and they're maxed out on 3-stream, 40 megahertz.
Some vendors use extensive CPU power on the AP, others use controller, so it depends, right?
Yeah. So we put a lot of focus on the power conversion circuitry. There's a significant portion of the money in that AP is on that power, on efficiency. So a lot of the standard kind of power bricks, not power bricks, power converters are running like 75, 80 to 85%. We're in the low 90s on efficiency, and it makes a huge difference.
It shows you the development time and effort we put into that AP. The little things like that.
How long did you spend to develop that?
So Tosh and I worked on it prior to the acquisition for about 3 months, and then 9 months after the acquisition. So it was 2 of us, part of our time, and then it was our full team on it for 9 months.
So realistically, it was about a 9-month program from start to finish. There was some concept and before the acquisition. So it's been one of the fastest product out in the market, hardware plus software, fully tested in 9 months.
That's pretty fast.
It helped that we were not the first company using that radio chipset.
Yeah.
Theros had worked a few bugs out. Because that's usually the time post in doing APs.
So you also do the low-level coding for the Atheros. So do you use the software provided by Atheros, or do you use your own, reflash it, or?
So Pankaj is our VP.
Yeah, so
you have to talk loud.
So Trapeze did a couple of things. Trapeze, when we acquired the company, they had a bare metal OS running on all of their APs, which is a for loop. Inside that, they would take the drivers from Atheros, standard reference drivers, and then they would modify them to make it work on their particular AP. 532 has that same OS. That was the fastest way for us to go back and get it out, the bare metal OS. So it's not the standard driver. We take the driver, we tweak it because we add our own secret sauce. As you all know, most of the reference drivers are Linux-based, and they flout rules completely. They go and make changes in kernel and so on, etc. We did not want to take that risk about doing changes in kernel and so on, and then not releasing it out in the open source world. We also wanted to focus on performance, so we did a lot of work internally about what to do when we get a packet, switch it back in the same stream without having it go through too many context switches and so on. And so that's what we did with the bare metal OS. With the 321, 322, we actually changed the OS. We went back to Linux. The goal was to go back and optimize on the drivers, standard reference drivers that we get from Atheros or Freescale, whoever that we use. But we did a lot of optimization on top of that as well. So we don't end up using the standard drivers. We do more optimization on top of that in order to get the best possible performance out of the software.
Okay. Thank you, Jay.
Thanks. Thanks, everybody.